So now we cover another example about electric fields. So say you have electron and proton and they are falling through an electric field. So minus E denotes the electron, it is going towards the positive plate, and plus E denotes the proton, it is going towards the negative plate. So the force acting on the electron and the proton are in the opposite directions. So for the time being, we ignore gravity, and we know force is equal to mass times acceleration. And this force is given as Q times E, where E is the electric field. So first we talk about electron. So we are going to ignore the direction. We know electron and proton are going to move in opposite directions. So the force, we will just take E times capital E, where capital E is the field, which is equal to mass of electron times acceleration of electron. For the proton, you take E times E as mass of proton times acceleration of the proton. So you can compute acceleration of electron as EE over mass of electron, and acceleration of proton again as EE over mass of proton. Notice that if you had taken electron as minus E and proton as plus E, then you would get acceleration with opposite signs, which is fine because they are moving in opposite directions. So notice that the distance formula is given as S is equal to ut plus half at square. So if initial velocity is 0, S is equal to half at square, and then you can rearrange this. So saying distance traveled is just the height or the distance between the plates, this would imply that the time is given as square root of 2s over a. But instead of s, we will write h. So time is given as square root of 2h over a. So you plug in this formula here. So time for the electron to travel is square root of 2h over acceleration of electron, and time for proton to travel is square root of 2 times h, that is distance between the plates, divided by the acceleration of the proton. So notice that if they were falling under gravity, if electron and proton were falling under gravity, then the time taken would be different. So in that case, the time taken would be square root of 2h by g. So for comparison with gravity, you can see that the time taken is square root of 2h divided by g. So notice that this is independent of mass. But here, for example, for proton, you put in the value for acceleration, you get square root of 2h times mass of proton divided by small e times electric field, and this depends upon the mass of proton. So now the question is, we started by ignoring gravity. So is it justified to ignore gravity? Can we actually ignore gravity? So let us see this. So you know, acceleration of proton we calculated to be small e times capital E divided by mass of proton. And let us compute its value. If the electric field is say given to us as 1.1 Newton per Coulomb, so that is the units of electric field, we will come to it in a bit. E is, we already know, is 1.6 into 10 to the power of minus 19 Coulomb. So mass of proton is 1.67 into 10 to the power of minus 27 kg. You plug these values in, and you will get, so this is approximately equal to 1 into 10 to the power of 8 meters per second square. Now that is very large compared to the acceleration due to gravity, and acceleration due to gravity is just 9.8 meters per second square, and compared to that, the acceleration of proton is 10 to the power of 8 meters per second square. So we can definitely ignore gravity. Now we want to talk about units. So units of electric field. So we know electric field times the charge is equal to force. So this force is always in newtons. So you can rewrite this as electric field as force over the charge. So the force is in newtons, the charge is in coulombs, so Newton coulomb inverse, and then you can write that as Newton as kg meters per second square, and then you have again coulomb inverse, and for coulomb we always write A. So you have m for kg, L for meters, for seconds you have t to the power of -2, and for coulomb we have A to the power of -1.